In the previous video I covered, I did a video on the molecule triphenylphosphine oxide, okay, which is this thing here. An alkene and triphenylphosphine oxide. In this video I want to go over the actual structures of the structure of the bonding in this molecule in triphenylphosphine oxide. So triphenylphosphine oxide are basically I'll just uncover the whole of that. So it contains lots of sp3 hybridized orbitals. So you got the phosphorus atoms in the middle, and then each of the benzene rings coming off like that. And the phosphorus is sp3 hybridized, which means and there's a lone pair of electrons here above it, which basically is in the p orbital, and that's sp3 hybridized. And when the phosphorus joins to each of the carbons on the benzene rings, this is what's actually called a sigma bond. So the phosphorus and carbons, the s orbitals overlap. These are s orbitals, and this is what's called a sigma bond. Okay. In contrast, when p orbitals overlap, you get pi bonds. So yeah, this is the basic structure of it. You get the phosphorus is sp3 hybridized, which means the s and p orbitals overlap and combine. It has to be explained in a separate video. And in the Wittig reaction, which I explained before, the whole thing is driven by the creation of the phosphorus oxygen bond in the triphenylphosphine oxide. This is what drives it. So you've got an enthalpy of creation, an enthalpy change of 575 kilojoules per mole, which is the bond energy. So to break bonds you have to put energy in, which is why this is positive. To make them you release energy, which gives you negative values. And this phosphorus oxygen double bond is one of the strongest bonds that exists. It's similar in value to other bonds like the beryllium fluorine bond, which is 573 kilojoules per mole to create. That's the bond energy, and the hydrogen fluoride bond, hydrofluoric acid, which is 568.6 kilojoules per mole bond energy. So when it comes to phosphorus and molecules, phosphorus usually creates molecules. Phosphorus can have 5 bonds, it's got a valency of 5, okay? So this is triphenylphosphine oxide, 1, 2, 3, 4, 5 bonds. There are other molecules and ions which contain phosphorus which have the same number. So these are examples. This is the phosphate ion. So the phosphate ion, it's got phosphorus with 1, 2, 3, 4 oxygens around it, 1 double bonded oxygen and 3 negatively charged oxygens, singly bonded. Okay, and DNA, this will be familiar to everyone. This contains a similar phosphate-like ion. It's not quite phosphate. Well, it kind of is because it's got, these are just bonded carbons. So you got the pentose sugar ring with the cytosine attached, bonded to oxygen, bonded to phosphate, double bond oxygen, negative oxygen coming off, then bond to oxygen, and then bond to the next pentose ring attached to guanine, and so on. So this is again 1, 2, 3, 4, 5 bonds around phosphate. Then you got tetraalkyl phosphonium ion, which is phosphorus with 1, 2, 3, 4 R groups around it. These can be carbon chains or rings. or even benzene rings, and it's got a positively charged phosphorus. And then you got this phosphenic acid, which is a bit like carboxylic acid. You got a phosphorus with O, oxygen, OH attached to it, and then two R groups. If this was a carbon, it would be a carboxylic acid, but because it's a phosphorus, it's a phosphenic acid. This is actually new to me. And then, so these are all examples of phosphorus attached to carbons with single bonds. Some of them are anyway. This is actually phosphorus single bond to oxygen, but in each case phosphorus has 5 bonds. That's actually, the phosphorus has 4 bonds, but it's a positively charged phosphorus. But here it's got 1, 2, 3, 4, 5 bonds. But for a long time it was thought that phosphorus could not be double bonded to carbon atoms, okay? Until somebody with Harry Kroto came along that showed this is not true. He got the Nobel Prize in Copley Medal for creating carbon-60. So he created this molecule, which is the first molecule to contain a carbon diphosphate double bond. And he also created this one, which is CH2 double bond PCl. This one is CH2 double bond pH. So he created the first molecule with a carbon phosphate double bond and showed this double bond rule was not true. He also created this reaction as well. CH3CH2 PCl3 gets converted to CH3C triple bond to phosphorus plus 2 hydrochloric acids. And there's also some other molecules which are contained with where you have phosphorus with 5 bonds. So you got the phosphate esters, you got phosphorus with OR coming off OR, OR. So this is bond to oxygen and bond to an R group, bond to oxygen, bond to an R group, and bond to oxygen, bond to an R group. And you've got a double bond to oxygen. And then this is the ilids, which is part of the Wittig reaction, where you got phosphorus with 3 bonds to benzene rings, and then double bonds to C, phosphorus double bond to carbon and H2. So that's the ilids in the Wittig reaction. I presume this was discovered before this, because this is carbon double bond to phosphorus. That's carbon double bond to phosphorus. I presume this was discovered later, but I don't actually know the history. But it must have been. If that's the first one, this must have come later. So yeah, this is yeah. So these are examples of. This is basically the structure of the phosphorus in triphenylphosphine oxide. So it's got this sp3 hybridized orbital and lone pair, and sp3 hybridized phosphorus. And these are all the various molecules which contain phosphorus with 5 bonds to various atoms, ions. Okay, that's my coffee, by the way.